Okay, we're going to start our final section here, and it deals with logistic growth. Logistic growth, and logistic growth is a really good model for population growth. Just think about the flu or something like that. It can only spread through so much of the population before everybody's got it. In order to integrate some of these logistical growth problems, we've got to learn how to do partial fraction decomposition. You may or may not have seen this before, but it's the process of taking a complicated fraction such as x minus 13 divided by 2x squared minus 7x plus 3, and setting it equal to two smaller fractions, okay? And those smaller fractions are going to be actually easier to integrate and use. So how does that work? Well, in order to do partial fraction decomposition, we have to be able to factor the denominator of our big fraction. And if the denominator doesn't factor, we can't separate into different fractions. So this guy, though, should work out. We've got 2x and x. We've got 3 and 1. And these are both going to be minus. So if you can't remember your factoring, go practice a little bit. This is going to come in handy for this section. And if you do remember your factoring, you need to get pretty comfortable rolling through it. All right? It'll just be less painful in the long run if your factoring skills are nice and sharp. So what we're going to do is we're going to take each of these pieces from the denominator and give them their own fraction. 2x minus 1 and x minus 3. All right. Now what we want to do is clear the entire fraction from the whole problem. Okay, we're saying that this is an equality statement, that the left-hand side equals the right-hand side, and if that's true, one of the easiest ways to solve a problem is to eliminate any fractions that are visible. So what I'm going to do is I'm going to multiply both sides of my problem by 2x minus 1 and x minus 3. When I multiply both sides of the equation by this, I follow all my rules of algebra. I haven't done anything illegal. It will clear the fraction out so that we're just working with the things in the numerator. Again, this is all based off of equality. So what I end up with is x over x minus 13 over 2x minus 1 times x minus 3 times 2x minus 1, x minus 3. And that goes away, and it's just going to leave me with x minus 13. And then on the other side of the equal sign, I have a over 2x minus 1 times 2x minus 1, x minus 3. And in this case, 2x minus 1's cancel out, and I'm going to be left with a times x minus 3. All right? And then b over x minus 3 times 2x minus 1 times x minus 3. So x minus 3 cancels out, and I'm wind up with b times x 2x minus 1. Okay, it's no different than if you had a fraction that looked like 1 over 3 plus 1/2 equals 1/6. If I multiply this entire fraction by 2 times 3, which is 6, and this is not a true statement, by the way, then notice that if I do that, I'm going to end up with 1 plus 2 equals, or I'm going to end up with 2 plus 3 equals 1, which is false, but that's the whole promise, where we're taking 2 times this first guy, 3 times this first guy, okay? It's the same thing that you did forever ago in Algebra 1. Okay, it's just nastier now because we've got a lot of fractions running around. Now, A is what we want to solve for. B is what we want to solve for. And we're going to use a little trick here because X can be whatever we want it to be. And I know that sounds really, really strange, but in the long run, X is our variable, so we get to pick it. We don't have an equals situation here, so X can be anything we want it to be. And if I'm trying to solve for A and B, I want X to make this guy right here a 0. All right? And in order to get that for this first one, I'm going to let X equal 3. And as long as I put that 3 in for every single X, I'm okay. I haven't violated any rules. And this is really a weird thing, but watch what happens. When I do that, I get 3 minus 13 equals a times 3 minus 3 plus b times 2 times 3 minus 1. And so notice that this a term goes away. All right. 3 minus 13 is negative 10. And then 6 minus 1 is 5. So I've got 5b. And when I finish this little step off, b equals negative 2. That's this b right here. Okay? That takes care of b. All right? The other thing that I'm going to do is I'm going to let this guy be 0 right here. I want this guy to equal 0. And so to do that, 2x is going to equal a half, or x is going to equal 1/2. All right? So I put 1/2 in for all of my x's. I'm running out of room here. 1/2 minus 13 equals a times 1/2 minus 3 plus b times 2 times 1/2 minus 1. And so notice on this guy, 2 times 1/2 minus 1, that cancels out because it becomes a 0, so he's gone. And I'm left with 1/2 minus 13. See, I need some space to work. I'm going to get rid of this guy right up here. So I'm going to finish this problem up here, and I'm going to have 1/2 minus 13. 1/2 minus 13 would be what? That would be 12.5. So 25 halves is equal to a times 1/2 minus 3. Well, that would be negative 2.5 or negative 5 halves. And so to finish this guy up, we would just multiply both sides by negative 2/5. So negative 5, because the 2's cancel here, the 5's cancel there, so negative 5 equals a. So this problem then would have b equaling negative 2 and a equaling negative 5. And so that's how, oh, this guy would be negative right here too, I guess. So he's going to be positive 5. All right, so how does that work? Well, to go back to our original problem here, our end result is that we can write this fraction now as a fraction, with a being 5, so 5 over 2x minus 1, plus b, which would be negative 2, so we could actually say negative 2 over x minus 3. So the process is kind of long. It's not horribly painful. There is a lot of algebra in it, and there's a couple of tricks that we probably haven't ever used before in here, especially down here when we try and figure out how to get a and b all by itself. But we're going to do this a lot through this section, and if you'll practice it, you'll get where you can see what needs to happen to get your partial fractions to work out. Trust me, in the long run, it's going to be easier to integrate this side than it will be to integrate this side.